Hello, today I'll be doing some problems from an old exam for the Chem for Allied Health majors, General Organic and Biochemistry. This is the OChem section, so I'll show you a screenshot of the different problems we'll be doing, and the first problems we'll be doing will be from problems 1 through 4, which deals with nomenclature or naming of organic molecules. And there is a test bank in this, but don't expect to get that for your test. That was a special circumstance. You should be able to know how to write it out, and it won't be as simple as that. So, number 1, we have a compound, and I'm going to draw it in the line formula. And this is, here's 1, 2, 3, 4, 5 carbons. On a 5-carbon chain, I start off with a very easy problem. We just count the carbons, 1, 2, 3, 4, 5. We have no branches, no substituents. So the name of this compound would simply be pentane. For number 2, we get a problem that has a little bit more branches. So I'll draw it how it's written on the exam. CH3, CH2, So this is how the problem's written. If we were to draw this in line formula, it would be something like 2, 4, 6, 7, 2, 4. And we'll have a methyl coming off here, and a methyl there, then a methyl there, and a methyl there. 1, 2, 3. That's actually drawn wrong. Let's erase that. Let's just look at this one over here, and we'll talk about it after, okay? So in this case, we'll start our numbering over here, and we'll do carbon 1, 2, 3, 4, 5, 6. If we were to try and branch out here, I start here, it gives us the same numbers, so that works out all right. So it's a 6-carbon chain, so that's going to be a 2, 4, 6. It's going to be a hexane. And we have substituents coming off. We have methyls coming off at 2, 2 methyls coming off at 2, and 2 methyls coming off at 5. Oh, actually, that's where I was wrong, okay? Let's just do this one, and then we'll do, so this is a bonus problem. This one has 6 carbons. We have methyls coming off 2 at position 2, and 2 at position 5. This would be 2, 2, 5, 5, 4 methyls, tetramethyl hexane, okay? So I drew this problem a little bit wrong. On the tests, the problem is more like this. Carbon, carbon, 2, 4, 6. So there's 6 carbons, but the one coming up here comes off like that. So what I forgot to draw in this one was there was an extra CH. This is a CH2 and this is a CH3. So when we number this, we can either number it 1, 2, 3, 4, 5, 6, 7, or we could do it where we start over here. So that would be our longest chain. 1, 2, 3, 4, 5, 6, 7. So looking at this, let's just say what the name would be in orange. When I number it in orange, I would say that this is a 7-carbon chain, so it would be a heptane. And then we have methyl groups coming off at position 3, 3, and 6, 6. So this would be 3, 3, 6, 6, tetramethyl heptane. Or if we use the pink, we have 1, 2, 3, 4, 5, 6, 7. We have a 2, 2, 5, 5 tetramethyl heptane. So the numbering system that we do, we're always trying to minimize our numbers. And 2255 is better than 3366, so this would be the incorrect one. And the proper naming of this would be 2255 tetramethyl heptane. Okay, let's continue to use this space on the board. Let's erase a little bit right here. But what we can do is the next one is a 6-membered ring, which has a methyl group coming off up here and an ethyl group coming over here. So in this case, we count the number of carbons in the ring, and we're gonna go, so this is an ethyl and this is a methyl. So we usually start with the the lower alphabetical number. So ethyl comes before methyl, so we'll do 1, 2, 3, 4, 5, 6. So this would be a 6-membered ring, so it would be called a cyclohexane. And then we have a 1-ethyl 4-methyl cyclohexane. Okay. The other thing is with 6-membered rings, they do have a special naming. When they're in 1-4 relation to each other, that is called para. So if you have the positions in 1 and 4, that's called para substitution. If we had substitution that was like 1 to 3 or 1 to 5, but since it's symmetrical, this one would be called meta substitution. And then lastly, if we have the positions right next to each other, like here and here, or 1-2 substitution, this is called ortho. So using these common names, we could have also called this compound here para ethyl methyl cyclohexane. The last problem, which I will do before I erase the whole board, I'll just do it right here. For number 4, what we have is we have a 3 carbons with a double bond from the 3rd carbon to the 4th carbon. 1, 2, 3, 4, 5, 6. Then we have 1, 2, 3, 4, 5, 6. We have 7 carbons total, and in between the 3rd and 4th carbon, we have a double bond. So with that, our naming system, we can either start at this end or this end. This end gives us a lower number, 1, 2, 3, 4, 5, 6, 7. So with this, it is a hept for the 7 carbons, but it's a heptene because there's a double bond in there. And then we need to indicate where that double bond is. And since we started on this end, we indicate the smallest number where the double bond starts. So this would be called 3-heptene. Moving on to number 5, what this question asks is to rank the following in order of lowest boiling point. So if this lowest boiling point, we would give a number 1, up to highest boiling point, we would give it a 3, since we're going to have 3 problems. And in part A, we have heptanol with the OL. We have heptane. And then we have heptanal, or anal. Okay, looking at this, so we have to first determine which one's going to have the lowest and which one have the highest. Since they're all hep, they are 7 carbon chains. But let's go ahead and draw each of these. So for heptanol, we draw 2, 4, 6, 7 carbon chain. And when there's no number, that implies that the alcohol is coming off of position 1. So we could draw it off over there. But since I'm kind of out of space, I'll draw it over here. So in this case, we have a 7 carbon chain with an alcohol coming off of number 1. This could also be called 1-heptanol. Heptane would just be a 7 carbon chain, 2, 4, 6, 7. And then heptanal would be a 7, 2, 4, 6, 7 carbon chain. And then what anal is an aldehyde, and what that means is on carbon 1, it has to be at the end. We're going to have a hydrogen over here like this. So we're going to have a carbonyl with a hydrogen. So in all actuality, if we were comparing three kind of equivalent, we should actually compare this, instead of with heptane, maybe with octane, because this one has a molar mass which is less. Even if we were to put an extra carbon on here and make this octane, it would still have the lowest boiling point. So my advice to you is, how do we determine which has the lowest boiling point? So like I said, if this had even an extra carbon, then they would kind of all have similar molecular weights, because these have the extra oxygen. So if we put an extra carbon, it would kind of even out the weights. But what we do is we look at what intermolecular forces are present in each of these three things. So let's start with heptane, the most simple. In heptane, the only thing available is dispersion forces. Okay? And once again, dispersion forces, which I'll just write like this, are present in all molecules. So we can say they all contain that. Now the next strongest intermolecular force would be dipole-dipole bond, dipole-dipole forces. And in this case, since it's all carbons and hydrogens are very similar in electronegativity, there would be no dipole-dipole. In this case, since we have a carbon-oxygen bond like we see here, we would have some amount of polarity. So this would have dipole-dipole intermolecular forces. And once again, we have a carbon-oxygen bond. So we have dipole-dipole forces. Now, the last intermolecular force that's present is hydrogen bonding. And hydrogen bonding is when you have an OH or an NH bond. Obviously, there's no O's here, so there's none available here. In this one, we do have O's and we have H's. We have H's all around, but there's no O directly attached to an H. So this one does not have any hydrogen bonding. But since this one has an O directly bound to an H, this would contain hydrogen bonding. And since they're all about the same molecular weight and things like that, we look at their intermolecular forces. Oh, the thing to realize is the question asks, rank the following in order of, lowest boiling point to highest boiling point. So the more intermolecular forces you have, the higher your boiling point. So this one should be the lowest because it has the least, and the fact is it even has a lower boiling point. Even if it was octane, it would still be the lowest. Number 2 would be heptanol because it only has 2 of the 3 intermolecular forces, and heptanol would be the one with the highest boiling point because of all 3 intermolecular forces present. So this was problem A. Let's look at problem B. This one had pentane, pentanoic acid, and 2-pentanone. So we'll get a little bit of practice in drawing these molecules, okay? So let's go ahead and draw pentane. Would just be a 5-carbon, 1, 2, 3, 4, 5. Pentanoic acid would be 5 carbons, but it has a carboxylic acid, and with the carboxylic acids, they always need to be at the end. So we draw this molecule over here. 1, 2, 3, 4, 5. That's pentanoic acid. 2-pentanone would once again be a 5-carbon, 1, 2, 3, 4, 5. But on carbon 2, we have our ketone. So this would be our 3 compounds, okay? Once again, most likely what I should do is in the future, I'll probably compare pentanoic acid to maybe 2-hexanone to heptane, because then they would have similar molar masses. But based on molar masses, we would rank it 1, 2, and 3. And as it turns out, that's going to help with these. So let's just go ahead and talk about the intermolecular forces present in each. Pentane only contains dispersion forces. This contains dispersion forces, dipole-dipole, as well as hydrogen bonding, due to the fact that we have this OH present right here. This one has dispersion, dipole-dipole, but it does not have hydrogen bonding, even though it has O and it has H's, you know, on all these carbons over here. None of the O's are directly bound to the H, so there's no hydrogen bonding. So if we're ranking them in order from lowest boiling point to highest, we're going to go 1, 2, 3. And once again, this would be true even if this was 2-hexanone, which would do that, which would give these similar molecular weights. And if this was heptane, which would give this, now all three molecular weights would be similar, and that would be the kind of question you can expect to see on your exam. Okay, number 6 has to do with hydration reactions. And hydration reactions would be draw out all the possible products of the reaction of water with the following, and the molecules that we have to deal with is we have a double bond, CH3, hydrogens. We have this one. For part B, we have a ring, the CH3 right here. For part C, we have another ring with methyls coming off. Oops. Coming off right here. Okay, for this problem in a hydration reaction, you can think of when you hydrate yourself, what do? You add water. So what we do in hydration reactions is we add water to a double bond. So a way to think of it is, in general, we're going to add water. So we're going to add water. But I like to say, instead of drawing H2O like that, we're going to add water in the form like this, where whenever we have a double bond, what's going to happen is one side of the double bond will get the OH, and the other side will get the H. So that's just a general explanation of how we do this. So in this hydration reaction, we can either add the OH right here and the H right here, which would give us this product right here. Or we could add the OH the other way, where we add the OH to this side of the carbon and the hydrogen to this side, in which case our product would be so we have our H being added right here. I'm going to move this OH to right there, hydrogen right there. And this hydration reaction, because it's unsymmetrical, will give us two different products. On this one, once again, we're going to be able to add the OH to one side and the H to the other, in which case we would get this product right here. And we can draw the hydrogen on there, but what really happens is we don't need to draw every hydrogen on there, so I'm going to leave it off. Just for your information, we add the H to one side of the double bond, we add the OH to the other, and we get rid of the double bond. Notice how the double bond is being gone. So then our other option would be to add it where the OH goes over here and the H goes over there, in which case we get this product over here. Okay, this last one, if we look at this molecule, there is a plane of symmetry going about this. So in this case, whenever we have a symmetrical alkane, we will only get one product, because if we add the OH to this side, or we add the OH to that side, it gives us the same product. I will show you. So this is where the double bond was. If I add the OH over here, and we don't have to draw in that hydrogen, but an hydrogen does get added to this position over here. This would be the exact same if we drew this compound with the OH going right here. And we can almost take this molecule and flip it over, and we see that it's the exact same molecule. So I do not want you writing both of these, okay? You will lose some points if you write both of them because they're the same compound. So in this case, with symmetrical alkenes, you only show one product, okay? Let's do a quick review. If we were to name this compound, we would start with our 1 on the alcohol. 1, 2, 3, 4, 5. We would name this a cyclopentane, but there's an alcohol at position 1, so cyclopentanol, and we call it 2,4-dimethyl cyclopentanol. Okay? The fact that it's cyclopentanol, we don't need to say 1 is where the alcohol is because that's implied in the naming. This one, once again, would be 1, 2, 3, 4, 5. This would be, this is also a 5-membered ring, so this would be 3-methyl cyclopentanol. And this one up here would be 1, 2, 3, 4, 5, 2-methyl cyclopentanol. Okay. Naming these ones, we want to find the longest carbon chain. 1, 2, 3, 4, 5. It's a 5-carbon chain. If we start the carbon chain on this side with 1, 2, 3, 4, 5, we get the alcohol at position 3. If instead we started it over here, we do 1, 2, 3, 4, 5. And this one, we still get the alcohol at 3. So either numbering order doesn't really change the alcohol, which is the main substituent. But notice how in pink we would get 2-methyl 5-pentanol. Whereas in yellow, it would have been 4-methyl 3-pentanol. And we want that number to be as low as possible, so that would be 2-methyl 3-pentanol. For this one, we would have to start the number here, 1, 2, 3, 4, 5, in which case this would be 4-methyl 2-pentanol would be the name of that. Okay? Okay, this next problem, number 7, has us arranging the following in order for most soluble in hexane. So in this case, we're talking about a polar solvent. The most soluble in hexane would be number 1 to the least soluble in hexane would be number 3. Okay? So for both of these problems, for A, I actually draw out the structure, and we have a 2, 4, 6, 8, 10. We have 1 decanol. 2, 4, 6, 8, 9, 10. So we have decanol. We have, let's see, 1, 2. This molecule would be called 1,2 ethanediol. 1,2 because there's 2 carbons, and off position 1 and 2 is the alcohols. It's 1,2 ethanediol. It's kind of a weird name. I wouldn't really expect you guys to know how to name that. And then the last one would be 2, 4, 6, 8. We have 2-octanol. 2, 4, 6, Okay, and we have an alcohol coming off at position number 2. So in these cases, what we really want to look at, they all, if we were to list the dispersion forces, they would all contain dispersion force. If we wanted to list intermolecular forces, they all contain dispersion forces, obviously. They all contain dipole-dipole, and they all contain hydrogen bonding. So what we're going to look at is the number of alcohols. So in the case of this middle one, it has 2 alcohols, whereas the other ones have 1. The more alcohols, the more soluble in water, or the less soluble in hexane. So that leads us to this one right here being number 3, because it has 2 alcohols, which are very insoluble in hexane. Okay. Now when we compare this one versus this one, once again, they have the same intermolecular forces, but this has an 8-carbon chain, this has a 10-carbon chain. The more carbons, the more soluble in hexane, and conversely, the more carbons, the less soluble in water. So the most soluble in hexane would be this longer carbon chain, and this one would be in the middle, number 2. Okay. The other questions we had were comparing 2, 4, 6, 7, 7 carbon chain, 2, 4, 7, and so this would be 2 heptanone in comparison to 2, 4, 6. This one I did it right, where I have a so in this case I have 2 heptanone, and in this case I have 1, 2, 3, 4, 5, 6. This is actually called hexanoic acid. So this is a 6-carbon chain, this is a 7-carbon chain, but because it has the extra OH, they're similar in molar mass. 2, 4, 6, and the last one has 2, 4, 6. It has hexane, but let's go and let's just leave it like that, okay? That's what the problem is. So in this one, we go back to intermolecular forces. This one only contains dispersion. This one contains dispersion, dipole-dipole, and hydrogen bonding. This one contains dispersion and dipole-dipole, but no hydrogen bonding. If we look at hexane, hexane is actually this molecule here. So hexane would be infinitely soluble in hexane, but the only intermolecular forces present in hexane is dispersion. So obviously this would be the most soluble. We would give this number 3. Now between this one and this one, since this one has extra intermolecular forces, that would make it less likely to dissolve in there, and that would give us this being, most soluble, most soluble would be number 1. So this one over here would be number 1. The most soluble in hexane would be hexane. Even if it was octane, to make it all comparable, it would still be the most soluble. This one would be the next soluble, and then the one that contains the hydrogen bonding would be the least soluble of these 3. Number 8 is a problem which is similar, but instead of saying arrange the following in order of most soluble, so this one is most soluble in water being number 1 up to least soluble in water being number 4. And the 4 things we have are octanol, we have butanol, we have butane, and we have butanal. Okay, so octanol is a 8-carbon chain, 2, 4, 6, 8, 2, 4, with an alcohol coming off. Butanol would be a 4-carbon chain with an alcohol coming off. Butane would be a 4-carbon chain, and butanal would be a 4-carbon chain with an aldehyde at the end. Okay, so which one would be the most soluble in water? Once again, let's put our intermolecular forces. This one contains dispersion, dipole, and H bonding. This one contains dispersion, dipole, and H bonding. This one only contains dispersion, and this one contains dispersion and dipole. So looking at that, water contains all three. It contains dispersion, dipole, and H bonding. Therefore, remember we always say like dissolves like. Things that are similar dissolve in similar things. So since this one has 3 intermolecular forces, this one only has 1, this would be the least soluble of the 4. Okay? Even if I made this longer, and as it gets longer, it gets less and less soluble. This one over here, compared to these other ones, doesn't have as many intermolecular forces, so this would be number 3. Now determining between these two, which one would be more soluble, they contain the same 3 intermolecular forces as water, but the longer the carbon chain, the more nonpolar it is. So this one would be a little bit more nonpolar characteristic than this one. So this would be number 2, leaving this shorter alcohol chain to be number 1. Okay, for number 9, what the problem asks is show all possible products of dehydration reactions with the following molecules. Some dehydration products might not be possible. So dehydration would be the opposite of a hydration reaction. In a hydration reaction, we took a double bond and we added OH and H to that double bond. In a dehydration, we take something that has an OH on one carbon and a hydrogen on the adjacent carbon, and we remove the OH and the H, so we remove water to give us a double bond or an alkene. Okay? So the first problem is pentane. Part B is this. This alcohol right here. And part C is this alcohol right here. Okay? So, first thing, we remember in dehydration, we remove water, make a double bond, make an alkene. Okay? In this case, this is pentane. It has no OH. There's no way for us to remove water, so this one would have no dehydration products. Okay, for part B, we do have an OH, so we're going to remove this OH. Now what I like to do is I like to mark the carbon that my OH is on. So in this one, we have this carbon here. So on the carbon next to it, does it have a hydrogen available to remove for a dehydration? And if we look, this bond here, this carbon here has 1, 2, 3 bonds. That means there's a hydrogen coming off over there. So what we can do in this dehydration is remove this OH and this H to give us water. So the product of this would be this right here. That would be the product of this. Now what we have to consider though is that OH on that carbon, is there a hydrogen on the other side? And we see that this carbon has 2 hydrogens. And whether we remove this one or this one, it doesn't matter. It'll give us the same product. But the product of this, when we remove this OH and this OH and this H, we would end up getting this product over here. And this would be the other product of that reaction. Okay? In this case, there's only 2 products for this dehydration reaction. Now in this one, once again, we do have an OH to remove, so we mark the carbon that the OH is on. Now this carbon does have an H available to remove, so if we remove this OH with one of these hydrogens, just one of them, we will get this product over here, And remember how we talked about when we only have 3 bonds, it becomes trigonal planar, so we can draw them kind of like a Mercedes sign. So this double bond is made there, but I'm going to draw it in this formation like that. And this would be the product if we remove that in pink. If instead we look at this carbon, if we remove this hydrogen here, once again, it will give us, so let's just do that one, okay? If we do this one, this will give us, instead now, the double bond goes to that one, it will give us this. Now, is this a little different? You might say there could be some cis-trans isomerism. If you look at it, this molecule can be flipped over, so you do not need to draw this product over here, okay? In fact, I don't want you drawing it because since these two are equivalent methyls, it doesn't matter which one it comes off, it's going to give the same product. Now, if we look at it as this other one, once again, this only has 2 bonds, so we have hydrogens right here. So when we remove, I'm sorry, I'm using pink again, this one and this one, that'll give us our product where we have CH3 and the CH3. That's these 2 CH3s right there. We have a double bond in between here, and we get that product right there, okay? So in this case, we have 2 different products. Let's just say, for example, that we change this problem up and we had made this instead of a methyl right here, let's say we had this as a isopropyl group. Okay, so this is a CH, this is a CH3, this is a CH3. Now, in this case, that would make this thing up here be a CH3, isopropyl, so we're leaving that isopropyl there. Now, in the case of this one, we can actually say that if it was an isopropyl, now we would have gotten a little bit different. Let's erase this whole thing. When we do this one in blue, if we remove, once again, this carbon, there is an H on the adjacent. If we remove the OH and this H, what we would get would be, this would be that methyl right there. This would be the isopropyl, but we would make the double bond right there. So in dehydration reactions, we do have the possibility of having 3 different products. Once again, we could have just had 2 products if we had something, but in this case, there's no alcohols. Just as another one to show you, if we had a carbon with an OH on it, but now if the adjacent carbons were something like tert-butyl groups, in the case of this one, this OH is on this carbon right here. This carbon here next to it has no H's since these are all methyls. This carbon has no H's, this carbon has no H's. That would give us no dehydration products also. So we'll get no dehydration products if there's no alcohol to remove, or if the carbon with the alcohol has no hydrogens on any of the neighboring carbon atoms. Okay? The last problem of the regular credit problems would be a hydrogenation reaction. So for number 14, this was called hydrogenation reactions. And basically, if we think about hydrogenation reactions, it says draw out all possible products of the reactions of hydrogenations using H2 with the following molecules. So we'll be hydrogenating with H2. And basically what we do is when we have an alkene, if we do a hydrogenation, when we add H2 in a certain fashion, it removes the double bond. Okay, so hydrogenation you can think of as remove double bonds by adding H's. Okay, so if we look at this, part A gives us this compound right here. Part B gives us this compound right here. And part C is one that's a little bit, this one is one that's really hard to draw. 2, 4, 6, 8. Oh, I did pretty good. So this is an cyclooctane with 2 double bonds on it, okay? So to determine the products of this, we remove double bonds by adding H's. So if we add H's there, our product will simply be wow, we took away the double bond. In this one, it becomes C. So we're going to add, let me just add the H's in another color. So we're going to add H2. We add 2 H's. This would be our product here. If you would just write, this would also suffice for the answer. And then for this one, we have 2 double bonds, unless I specifically say equivalence, where I say you only add 1 equivalent of hydrogen, you're going to assume all the double bonds get taken away, and this would simply just be that molecule there with the double bonds missing. If I said 1 equivalent, you could maybe just take away 1 or take away the other, but I probably won't do that. So this would be the hydrogenation reaction. Now real quickly at the end, there was 2 extra credit problems. Extra credit A said how many chiral centers are there in numbers 1 through 4? You can go back and look at those, and you should get a grand total of, pause it, think about it, 0. Okay, go back and verify that. For part B, it says draw all possible dehydrogenation products of the following compound. So in this one, we're going to be, if this is what you're going to do a dehydrogenation of, if a hydrogenation takes double bonds and removes them, what do we think a dehydrogenation is? Very good. It takes single bonds and it converts them into double bonds if there's 2 hydrogens available on adjacent molecules. So I'm going to draw my hydrogens. We have a hydrogen here. We have hydrogens right here. Hydrogens here. 2 hydrogens there. And then 3 hydrogens right here, okay? Let's say we're going to remove these hydrogens right here. That would give us this dehydrogenation product right there. What if we remove this hydrogen with this hydrogen? That would give us that dehydrogenation product right there. And lastly, let's see how orange does. If we remove this hydrogen here with this one, that would give us this one over there. And that would be all 3 dehydrogenation products. Do you have a question? Why can't we remove this one over here? Well, that's a good question. Let's see what happens. If we remove this one over here, the only adjacent hydrogen would be this one with it, and in which case it would give us this product right here. And in this case, we could flip this over, and this is a free rotation, so these 2 are equivalent, so you would not want to draw both of them since those things are coming off. Thank you very much for your time. Good luck studying for your tests. Have a wonderful night, day, or whatever time it is. Aloha.